So yeah, it's been like very late. I'm making the solution for this PDF. Like there were 5 questions I've sent. Yes, there were 5. So one by one we'll see like how to approach this question. So first, let me just snipping tool, just snip this thing. Uh, Snip the question and copy and paste on this. Yeah. So here we can see this question. So it is given that Mac is greater than 1 uh, upstream of this normal shock wave, and downstream we have some properties given here. Okay, and the question asks like choose which one of the option is correct. So we have to choose, like we have already studied about normal shock wave, right? So how properties change. Okay, so the first thing should come in your mind is whenever there is normal shock wave. Okay, so upstream, at the upstream, your Mach will be greater than 1. Okay, supersonic Mach, and after crossing the normal shock wave, it just falls down to subsonic. So M2 will be less than 1. Okay, just check somewhere like which option have M2 less than 1. Okay, so M2 is less than 1 here and here. Okay, and in A option, we can see like it is given M2 is greater than 1. So it can't be possible. Okay, so three things are possible here. B can also be right, C can also be right, D can also be right. Why B can be right? Because M2 is less than M1, that is true. And that is different thing, that whether it is mentioned M2 is less than 1 or not. Okay, but technically this thing is also right. Okay, so we have to see that thing. So now one option is eliminated. Now let's see how uh, the other properties varies. So we know that since M2 is dynamic property, like M is dynamic property, so M2 is decreasing. So that means dynamic nature is decreasing. So which will lead to static nature increment. Okay, so T2, P2. Okay, so these things will rise. Okay, let's see in which of the option we have T2 and P2 increased. So T2 is greater than T1. Yes, correct. T2 is greater than T1, and that is correct. And here P2 is greater than P1, P2 is greater than P1. So still we can't predict. Okay, so right now we can't eliminate any of the options till now. Okay. So other thing is that let's talk about total properties. So we know after crossing normal shock wave, due to irreversibility, that is kind of a friction in normal shock wave, we get P naught 2 less than P naught 1. Okay, and since it's a form of friction, so there is no heat addition, because normal shock is adiabatic. There is no heat addition, so T naught will remain same. T naught 1 will be equal to T naught 2. So now with these two properties, we have to decide which one of the options are correct. So T naught 2 is greater than T naught 1, yes, but P naught 2 is not equal to P naught 1, so B can be eliminated. B can be eliminated, and here we can see T naught 2 is less than T naught 1, so C can be eliminated as well. So now only option which is correct is this D option. So for the answer for this question will be D. Okay, I hope you got this. Yeah, so it will be D. Okay, let's see other questions. uh, Now just which are these? I'll just snipe it. Okay, so copied it and have to paste it here. Yes. So yes, in this question, what we have given is uh, m m1 is equal to 4. Okay, and there is normal shock wave, and m2 is greater than m2 is equal to 2 after normal shock wave. So first question asks is this condition possible? So we know that whenever there is a normal shock wave, so at upstream we'll be having supersonic Mach. But at downstream, it is a must thing that your Mach should be less than 1 subsonic. Okay, So the condition which is given to us is not possible. So answer for the A option is A question is not possible. And why is it not possible? Just give the reason. After crossing normal shock wave, your Mach decreases to subsonic. Your Mach becomes subsonic. Okay, so that is the cause that we are saying that this is not possible. This case is not possible. So let's see what is asked in the question after that. If not possible, then find the value of m2. So we know the formula for m2. What formula we have? Okay, so there is a normal shock wave. We know that m1 is 4, and when m1 equal to 4. So now we can calculate after crossing normal shock wave, what will be the Mach number. So we have formula m2 square equal to 1 plus gamma minus 1 by 2 m1 square upon gamma m1 square minus gamma minus 1 by 2. And since it's air or nothing is mentioned, you'll assume that it is talking about air. Okay, if you are talking about air, so your gamma will become 1.4. Okay, so let me just quickly calculate this thing. I'll use this calculator. So what we have, Mach is equal to 4. So using the formula, uh, 1 plus gamma minus 1 by 2 for air will come 0.2 into 4 ka square upon 1.4 into 4 square minus gamma minus 1 by 2, that will be equal to 0.2. Okay, now don't write this answer. Why? Because it's the value of m2 square. We have to find m2. Okay, so we have to take the root of it. Okay, so to take the root, I'll just uh, first press equals to, and then press this button, which is this root sign. So we'll be left with 0.435. So the m2 will actually be 0.435. Okay, okay. So now we got m2. Can we calculate other properties? Yes, we can calculate other properties as well. So what is asked? Now the question is asking. Now the C option is asking m2 equal to 0.435. Okay. Now the question C is asking what is the ratio of P2 by P1. So we have the ratio of P2 by P1. Okay. 1 plus 2 gamma upon gamma plus 1 m1 square minus 1. Okay. And it will be coming as 2.8 upon 2.4. This will be 16 minus 1. So 15 into 2.8 upon 2.4. So 15 into 2.8 upon 2.4 plus 1. So this will be a pressure ratio. So uh, the pressure after the normal shock wave is 18.5 times of the pressure which was before, and it is about total pressure. Okay, so it is 18.5 times now. Okay. So we got the pressure ratio. Okay, so let me just quickly make it like this and just remove all these things. So yeah, we got a C option as well, right? So now the question is asking what is your rho 2 by rho 1. So now as you have this 18.5, m2 is 0.435. Now using two ways you can calculate this thing. Okay, we have a formula for rho 2 by rho 1 equal to v1 by v2. Okay, which is equal to gamma plus 1 upon 2 m1 square upon 1 plus gamma minus 1 by 2 m1 square. Okay, okay, first formula is this. Okay, and this term is equal to m characteristic square. Okay, you can remember that thing as this, just this formula. So we can use this formula, and other formula we can use is rho 2 by rho 1. Since p2 by p1 is already known to us, so we can directly use this formula as well, which is 1 plus p2 by p1 gamma plus 1 upon gamma minus 1 upon p2 by p1 plus gamma plus 1 upon gamma minus 1. So this formula is also valid. Since we know two things, we also know M1 and we also know this P2 by P1 ratio. So both approaches you can try. Okay, so I'll be trying this approach because I know the values, and this particular value for air comes as, for 1.4 gamma value comes as 6. Okay, so I can directly write as 1 plus 18.5 into 6 upon 18.5 plus 6. Okay, so this thing will come as 1 plus 18.5 into 6 upon equal to upon 18.5 plus 6. Okay, so it is coming as 0.57, 4.57. Okay, so this ratio, this rho 2 by rho 1 will be coming as 4.57. So density has become 4.57 times of the density before normal shock wave. 4.57. Okay, now the question is asking this: what is the ratio of T naught by T1? Okay, so just remember the concept of normal shock wave. Okay, normal shock wave is adiabatic. We know that, and adiabatic means there is no heat exchange or heat transfer or anything. Nothing is happening. Okay, so since there is no heat exchange, so T naught 2 will be equal to T naught 1, and from where does it come? H naught 2 will be equal to H naught 1. Okay, so your energy is not changing, so we can relate that energy with T naught, right? So your T naught will not change, total temperature will remain constant, and that is the that is the property of our normal shock wave. The friction in the normal shock wave will cause irreversibility, and that irreversibility will lead to the entropy change only because of total pressure change. Okay, only because of total pressure loss. Temperature loss is not happening. So T naught 2 by T naught 1 we don't have to calculate, we can just use 1. Okay, now we have to see this thing. So P naught 2 by P naught 1, what will it come? Okay, so you might be thinking of the formula P naught 1 by P naught 2 equal to E to the power del S by R. Okay, but we don't know del S. Okay, we don't know del S, so we can't use this formula. Okay, if del S was given, you can directly inverse this thing. Okay, and then you could have got the answer, but right now del S is not given. So let's see how to approach this. Okay, so first you'll calculate P naught 1. Okay, how will you calculate P naught 1? So just before normal shock wave, see the properties. Okay, so P naught 1 by P1 will come out to be equal as 1 plus gamma minus 1 by 2 m1 square. Okay, up to the power gamma upon gamma minus 1. And similarly, after normal shock wave, it will become P naught 2 by P2 equal to 1 plus gamma minus 1 by 2 m2 square to the power gamma upon gamma minus 1. Okay, now you might be thinking, we don't know P1, we don't know P2, we don't know P2. So how to approach this question? So just suppose this equation is equation 1. Okay, first let's calculate what the values are coming, so it will be more easy. Okay, so I'll calculate the values for both sides. So m1 is 4, so 1 plus 0.2 into 16, 4 square. Okay, to the power 3.5, that is the value of gamma upon gamma minus 1 for 1.4 value of gamma. So it is coming as 151.8. Okay. So it is coming as 151.835, I think. Yeah. Okay. And let's calculate this right hand side thing after normal shock wave. So your Mach is 0.4 0.435. So 1 plus 0.2 into 0.435 का square to the power 3.5. Okay, so this value is coming. Okay, 1.14, 1.14, 1.14. Okay, so let me just calculate this thing again. 1 plus 0.2 into 16 to the power 3.5. Yes, that's correct. 1 plus 0.2 into 0.435 per square to the power 3.5. Yes, this is correct. Okay, so now you have two equations now, P01 by P1. This is your first and this is your second. Okay, so now what will happen? Okay, so now you just have to divide two things. Second by 1 you can do, okay, and first by 1 you can do. Both ways are correct. There is no particular way. Okay, but the ratio should be P02 by P01. You can either inverse whatever is coming after that. That is different thing. So I'll use 2 by 1 approach. Okay, I'll be dividing this second equation by this first. So P02 by P1, okay, will be divided by P1 by P0, will be divided by P01 by P1, right? This is P02 by P2, my bad. So it will be equal to P02 by P2 into P1 upon P01, right? Okay, so it will come as 1.14 upon 151.835. Okay, now what values we have? Okay, let's just send these things to right hand side. I'll just shift these things. Yeah, I'll just shift these things here, make it smaller. Okay. So yeah, so now using this, so P02 by P01, okay, and other things I'll be sending on the right hand side will be equal to P2 by P1 into 1.14 upon 151.835, I think. Yeah, whatever the values. Okay, so now we know the value of this P2 by P1, which is this 18.5. Okay, now I can use my calculator. So 18.5 into 1.14 upon 151.835. Okay, so this is the value of P02 by P1. Okay, so using this approach you can find out that thing. 0.13849898 is the P02 by P01 value. Okay, so we can see that your P02 is less than P01, and that is what we study while uh, while describing the properties of this, right? P02 is less than P01, and using the formula we are getting the same thing, same result, right? So yes, so now I'll just make these things vanish, and we have the last thing left is to calculate. Okay, this is equal to 0.1389. Yeah, so now you can also calculate the entropy change also, right? Using that formula P02 by P01 by P02 equal to e to the power del s by r. Now we have to calculate T2 by T1. Okay, so we know the formula for T2 by T1 is equal to P2 by P1 plus gamma plus 1 upon gamma minus 1 upon P1 by P2 plus gamma plus 1 upon gamma minus 1. Okay, okay. Either you can use this approach or you can directly use these two ratios. Okay, what you'll do, you'll just multiply P2 by P1 with rho 1 by rho 2. Okay, so you'll get T2 by T1. Okay, I'll use this approach. Try with this approach because this formula should be remembered by you guys. Try with this and compare what is the value. Okay, so I'll use this formula and it will be 18.5 into 4.57, 84.545. So T2 by T1 is 84.545. Just if I'm wrong, just confirm with this formula and you will get the same thing. Okay. So second question is done as well. 84.545. Yeah. So second question is completed. I hope you got the approach how to solve these, how to tackle these questions. Okay. So now I will move to the next slide, and this is our third question. This is our third question. So what we are given is that we are having a nozzle, okay, and uh, just tell me whether it's nozzle or not. Okay, just think of it and tell me, is it a nozzle or did I say something wrong? Okay, so I'll correct myself. It is not a nozzle because your entry flow is mag greater than 1, so it will see it as a diffuser. So your mag entering should be decreasing till some point. Okay, will be decreasing till some point. So that's a diffuser for it. And if it becomes subsonic in midway, so for that subsonic nature, it will see it as a nozzle. So it will start to accelerate from that point. Okay, I think that is what is asked in this question as well. Okay, so let's see what is given. M1 is given, which is 3, and M2 is given, which is 0.85. So your flow exit is this. Flow is exiting with this Mac. Okay, and in between we are having a section. Okay, and the question mentions that the flow is experiencing a normal shock wave. A normal shock wave. Okay, and this diameter is given D1, which is 0.5. Okay, and flow is entering with Mach equal to 3, and if flow is leaving the duct with this Mach, so Mach in front of the nozzle is this. Okay, so Mach front means this part. Okay, this upstream part. Don't see that Mach will be facing this way. No, Mach faces this way, and this is the back of not Mach. This is normal shockwave. Just correct it. Normal shockwave back is this. Okay, and this is front. So upstream of the normal shock wave, this is upstream of the normal shock wave, your Mach is equal to 1.5. Okay, so the question is asking what is My. So My is this is your Mx. Okay, so the question was looking complex, but as we read this part, so just because of it we can solve the question A. Okay, so A, what you'll do, the same thing. Just think of it as Mach after the normal shock wave, which is M2 by which we denote, and this is upstream Mach for it. So this will become your M1. So My square will be equal to 1 plus gamma minus 1 by 2 mx square upon gamma mx square minus gamma minus 1 by 2. Right? So now what you'll do, you'll just put 1.5 in this place. So let's do that. So 1 plus 0.2 into 1.5 square, okay, divided by 1.4 into 1.5 square minus gamma minus 1 by 2, which is 0.2, right? So now this is not your answer. You'll have to take a root of it, right? So press the root sign now. And this is your my value. This is your my value. So my will come as 0.7701. So first question is solved. So see, like there was so much data given initially, but just by this line we can approach the question. Just by this line. Okay. So sometimes the question will be framed this way, like very lengthy, but the question will be so easy for that. Okay. It might look lengthy and people just get drained out quickly. Okay. So don't think that way. Just read the question. So there will be some, there will be like easy thing given there. 0.701 was the max. Yeah. 701. So we don't have to like give up on the question. We can leave it for that particular moment, okay, and solve it later. But yes, reading it and solving it first be benefited, can be beneficial. Yeah. So now the thing is we have to calculate a3 by a1. Okay. So how will you approach the a3 by a1 thing? Okay. So think of it. Okay. So a3 is a point where your normal shock is at. Okay. This is your a3. This is your a1 and this is your a2. That is what is mentioned here. Okay. So now you might be confused, like which Mac to use, to calculate A3 by A1, because we have two Macs at this point, one upstream of the normal shockwave, one at the downstream of the normal shockwave. Okay. So I will suggest that use upstream thing, like this much particular part is your isentropic and this much particular part is your isentropic, just before and just after the normal shockwave. Whole nozzle is not your isentropic. So just before normal shockwave, right? So your mac will be this mx. Okay, if you are relating with m1, that will come in a3 by a1 formula, right? So these two max will be used because we don't need to deal with normal shockwave. That is a different thing. That is not a part of area calculation, because for area calculation we use isentropic relation. Okay, isentropic relation. So like this much nozzle is isentropic, this much part is isentropic, not nozzle, and this much part is isentropic, not the whole part. Okay, because as your normal shockwave is coming, it will become irreversible thing. Okay, so a3 by a1 will be equal to at a1 there is 3 mac upon, and at a3 is your mx mac, which is 1.5. Okay, 1 plus gamma minus 1 by 2, 1.5 ka square upon 1 plus gamma minus 1 by 2, which is 3 ka square, to the power gamma plus 1 upon 2 gamma minus 1. This is your formula. Okay, so this gamma plus 1 upon gamma minus 1 was our 6, right? And it is being divided by 2, so it will come out to be 3. This value will come out to be 3. So I'll just use the cube thing. You can calculate it by yourself. I'm just using everything for air. 1 plus 0.2 into 1.5 ka square divided by 1 plus 0.2 into 3 ka square. Okay, and this uh, 3 ka square to the power 3 into this uh, 3 by 1.5, which is equal to 2. So I'll just multiply 2. So this is your value. A3 by A1 is 2.78. A3 by A1 equal to 0.278. Okay, and you can see like A3 is less, so it is validating that point. Okay, yeah. So now let's see what is being asked on the next page. 0.278, right? 0.278. Okay, and similarly you'll do for A3 by A2. Okay, so what you'll do now, you don't have to take the mx, you'll be taking my. Okay, you'll be taking my. So A3 by A2 will be equal to this, what's the mac at the A2, which is 0.85 upon this uh, 0.701, yeah, my. 1 plus gamma minus 1 by 2, 0.701 ka square upon 1 plus gamma minus 1 by 2, 0.85 ka square to the power 3. Okay, so quickly calculating that, 1 plus 0.2 into 0.701 ka square divided by 2 into 0.85 ka square, right, to the power, it will come as 3, and we have to multiply 0.85 divided by 0.701. Okay, so you will be getting this area, 1.072. A3 by A2 is equal to 1.072. So it is validating that, because A2 is less, A3 is more, so it will come more than 1.07. Okay, using the area ratios we can calculate these things. Let's see what is being asked in D point. So in D, is the flow isentropic? So as I mentioned, it is kind of an incomplete question, but you can say subjective answer, like not subjective but objective. Okay, so if you are talking about whole, okay, whole nozzle or whole duct, that's a better word, whole duct. So it is not isentropic. It is not isentropic. Why? Because normal shock is coming in between. So normal shock wave is making it irreversible. So irreversibility has come. So it will become non-isentropic. Okay. But 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 let's suppose this. Here you have normal shock wave. Okay. If you are talking about this region, okay, so it is isentropic, because normal shock is not coming in the picture for this much particular portion, and similarly for this much particular portion. So that's why we can use A2 by A1 formula for this and this separately. We couldn't use like A3 by A1 by A2 thing directly. Okay, but using these two we can get that value. But that's the whole point. These two values are only valid for the part which is reversible and adiabatic, that is isentropic. Okay, so you can say like this. You can say like this: whole complete duct is non-isentropic, but a region of M1 to Mx is isentropic. Okay, and region of M My to M2 is isentropic. Or uh, just before and after NSW, your things become isentropic if there is no other irreversibility present. Okay, so that's the whole cause of it. If you want to show that in diagram, do show that. Okay, I'll do that here. So this much part is isentropic, and this much part is isentropic, not the complete. Yeah. So now let's see, if answer to D is no, why so? So we have given the reason. So these two questions are completed. Okay. So what properties we are we are getting constant. Okay. We are going to be okay. What properties are going to be constant throughout? Throughout. So it is talking about throughout. Okay. So it is taking the whole duct and asking like what properties will remain constant from the inlet to the outlet. Okay, even after crossing a normal shock wave. So the only constant properties are T naught. Okay, so T naught 1 equal to T naught 2 equal to T naught 3, T naught x, or like anywhere present in the duct. And similarly, from where this thing comes, it comes from energy conservation, which is equal to H naught 1 equal to H naught 2 equal to H naught 3, and at any point. Okay, so these two properties, total enthalpy and total temperature, are going to be constant throughout the nozzle, are going to be constant. So yes, so the all the questions are like completed for third question as well. So now moving to the fourth, let's see what is being asked here. Okay, good. Copying it and we'll be pasting it here. Okay, so air is flowing through a duct. Wait, I'll just okay. So air is flowing through a duct with a constant area pipe. Okay. So if constant area comes, so you can think of either Rayleigh flow or Fanno flow. Both are possible if this much data is given. Okay. So now the question says air is flowing supersonically. So entry, or like let's take a part of the pipe. So air is supersonic at first, greater than 1. Okay. If at a section x, so at a section x, okay, the flow experiences a normal shock wave. Okay, a normal shock wave. So here we drew like this section is of normal shock wave. This is a normal shock wave. Okay, and better to draw with this red color. This is your normal shock wave at x section. Okay, the Mach at that point was 5. So since the flow is experiencing normal shock wave, and this is not mentioned whether the Mach is for upstream or downstream. So we can use our logic. We know that after crossing normal shock wave, your Mach becomes less than 1, right? So whatever the Mach is present at that point, it will be upstream of the normal shock wave. So here, okay, here Mach is given, which is m equal to 5. Okay, because we know that after crossing normal shock wave, that Mach gonna fall to subsonic. That's the nature of this normal shock wave. So Mach is given for upstream, just upstream point of that normal shock wave. Okay. Okay. So calculate the maximum length of the pipe downstream normal shock wave. So from this portion to this, maximum means we have to calculate to the point where we are reaching Mach equal to 1. Okay. So we have to calculate L max only. Okay. So after normal shock wave, what length will be needed to make the Mach 1? First, for that, for calculating this length, we should know what is the Mach at this point, right? So what to do? We can use normal shockwave relations, right? So now we'll do that. Okay, I'll just make sure everything is cleaned up. Yes. So we were given a pipe, okay, at a section. There was Mach equal to 5 and the flow experiences a normal shockwave. So after that, I'll name that 1. Okay, I'm just naming this part as M, and I'll name whatever the part is after normal shockwave as 1. So we have to calculate this M1. Okay, after normal shockwave, what is the Mach we are getting, and then we have to calculate this much length till we reach Mach equal to 1. Okay, this is your L max. Okay, first let's calculate the M1. So M1 square equal to 1 plus gamma minus 1 by 2 M square upon gamma M square minus gamma minus 1 by 2. So this M is your 5. This M is your 5. So 1 plus 0.2 into 25 divided by 25 into 1.4 minus 0.2. Okay, so this is not your answer. You have to take the root. Okay, you have to take the root. So this is your Mach after normal shock wave, 0.415. So M1 is coming as 0.415. Okay, so now we can calculate our length because all things are given to us. Okay, 0.415 we are getting. So now we can draw whatever the duct we have after normal shock wave. So flow is entering with M1 0.415. This is the story after normal shock wave, because before that, like from this including this normal shock wave, we don't need whatever the present whatever is present upstream of this. Okay, and here we are getting M1, and this is your L max. So L max we have to calculate, and I should check like what is given. So F is given, pipe area is given, so I can directly use the formula 4 FL max by D equal to 1 minus M1 square upon gamma M1 square plus gamma plus 1 by 2 gamma ln of M characteristic max square, that is gamma plus 1 by 2 M1 square upon 1 plus gamma minus 1 by 2 M1 square. Okay, it is inside the log. Okay, so now I have to calculate this L max from here. So how I like to solve this question is first solve this whatever is present inside the log, then take the log of it, then multiply this portion. Okay, so I'll just write things here. Okay, so before that you have to calculate the diameter because you are not given area. Okay, so pi by 4 d square equal to 2. Okay, so d square will be equal to 4 into 2 upon pi ka root. Okay, and this d will be equal to this, so 8 by pi root. So 8 by pi, and we'll be taking the, so 1.6, around 1.6 is your diameter, and this is in SI unit. Okay, you should check that. So diameter is equal to 1.6 meter. Okay, so now I'll use the second pen, and first I'll calculate this portion, then I calculate this portion. So this gamma plus 1 will be 2.4, gamma plus 1 by 2 into m1 square, that is 0.415 square divided by 1 plus 0.2 into 0.415 square. Okay. Okay, now I have to take the log of it, ln into it was gamma plus 1, so 2.4 divided by 2.8. Okay, so this thing is coming 1.38, which is of negative. Okay, So this is negative of 1.38. So 1.38. Now I have to calculate this part, which is 1 minus m1 square. So 1 minus 0.415 square divided by 1.4 into 0.415 per square. Okay, so this part is coming here, 3.433, 3.433, 3.43 you can write. Okay, so we got these two. Now we can subtract these two. Okay, and like, you know the value of f, you know the value of like 4 is constant, so d, you know the value of d. So your this value will be coming as 3.43 minus 1.38. 3.43 minus 1.38. So this value is 2.05. Okay, so solution, this part is 2.05, and like I have to calculate L max. So L max is equal to 2.45. So D will be multiplied here upon 4F will come downstream of at the denominator of it, 4 into 1 0.016, and this D value is 1.6. Okay, so now calculate this, you'll be getting your L max. So into 1.6 divided by 4 divided by 0.016. So this much length you need to reach to that Mach. Okay, so it is coming out as 51.25 meters. Okay. Okay. So this was like a question framed by me, so that's why this value is coming this big, uh, because I made this area of 2 meter square. Okay, yeah, it's correct. So 51.25, 51.25. So doing all these, whatever the story was, you'll be getting your 51.25 length after the normal chalkway, 51.25 meter of length. Okay, and do remember SI units. Okay. So now let's see what's the last question. I'll just take the snapping tool, snip it, and copy, and we'll paste here. So now let's see what is being asked in this question. So we are given with a duct which is looking like a constant diaduct, and heat is being added. So since it's a constant diaduct and heat is being added, so you should know that it's a Rayleigh flow. Okay, so in Rayleigh flow we have heat transfer, but we don't have friction. Okay, so T1 is given, M2 is given, M1 is given, and heat addition is there. We don't have this, but what amount of heat is being added. And the question question is saying that what is your T2? Okay, what is your T2? Okay, so let's think on it. What is your T2? Okay, so if you remember, we have noted down some formulas for it. So T2 by T1 for Rayleigh flows, it comes out equal to be your M2 by M1, 1 plus gamma M1 square upon 1 plus gamma M2 square to the whole power square, to the whole square. Okay, so this is your relation of T2 and T1. So T2 can be calculated with this form. So T2 will come out to be equal as T2 by T1 will come out as m2 is your 1, and m1 is your 3. So since supersonic flow is entering, it is being like reduced to Mach 1, right? So heating effect is going on, right? We have discussed this in Rayleigh flow, like using this chart, using this TS curve. We knew that on heating of subsonic it accelerates, but on heating of supersonic it decelerates, and both form reach to Mach equal to 1 on heating. But if you are cooling down both of them, so your subsonic will get slowed down and your supersonic will get more speedy, more accelerated. Okay, so 1 plus 1.4 into m1 square is this 3 square upon 1 plus 1.4 into 1, okay, and this whole square. So I'll just calculate this quickly. 1 plus 1.4 into 9 divided by 1 plus 1.4, which is 2.4, right? And it is multiplied with, it is divided by 3 and being squared. So this is the value. Okay, so this is the ratio of T2 by T1. Now I just have to multiply what is the value of T1 to get T2. Okay, so into 400 I'll do, and I'll be getting what is the temperature at the exit of the duct at the section we are given where Mach is 1. So 1427 is the temperature, 1427.16. So T2 is coming out as 1427.16. So we can see that temperature is being increased, so heat is being added, and it is following all the natures we have already discussed while studying Rayleigh flow. So 1427.16 Kelvin. Okay, Kelvin. You should also check, like you should first read all the things given in the question, because since it is mentioned air and I'm directly using 1.4, let's suppose it was something else and I didn't read this part. Okay, it was like, let's suppose it was CO2. Okay, then it could have been a trouble for me because the answers I'm putting, it would have been wrong for that point. Okay, so first you should know, like, is the fluid given? If not, you can use 1.4, and if it is given, you should see like which fluid is given and what gamma value shall I choose. Okay, now we have to see what is the heat amount we have added. Okay, so Q will be equal to your Cp. Cp I'll use, like since it's air, so Cp is 1005. Cp T naught 2 minus T naught 1. Okay, so this difference will give me how much heat we have added. Okay, what does this mean? Like we'll be having some total enthalpy here. So H naught 1, we can use this much part as well. First we have to calculate what is T naught, T naught 1. So T naught 1 by T1 will be equal to 1 plus gamma minus 1 by 2 m1 square, which is 3 square. Okay, and since same for T naught 2, T naught 2 by T naught T2 equal to uh, 1 plus gamma minus 1 by 2, 1 ka square. Okay, so this value will come out to be 1.2, and I have to calculate this part. Okay, both parts. So 1 plus 0.2 into, this is 3, right? 3 square. Okay, now I have to multiply this T1 here, so into 400. So 1120 is your T naught 1. T naught 1 is equal to 1120 Kelvin. What is your T naught 2? It will be 1.2 times of 1427.16, so 1712.6, 1712.6, 1712.6 Kelvin. Okay, so these are your T naught 1 and T naught 2. Now let's calculate what is your h naught 1. So h naught 1 will be equal to cp t naught 1, and h naught 2 will be equal to cp t naught 2. Okay. Okay, so this is your values for h naught 1 and h naught 2. Now there will be some difference. Okay, so the difference they'll be having, okay, using that difference we can know how much heat is being added, how much heat did the flow got. Okay, and since these are your small h, so it will be joule per kg only, specific. Okay, so now I can say that I can use the equation like h naught 1 was present. Okay, when heat was added to h naught 1, it became h naught 2. Using this story, I can frame, like I can crack all the problems even when I'm talking about engines, combustion chamber. This thing can be done there. Okay, so now I can calculate Q. Q will be equal to h naught 2 minus h naught 1, which will be equal to Cp 1712.6 minus 1120, and Cp value is 1005 joule per kg Kelvin. Okay, so this minus 1120 into 1005. So this is your heat added to the system. Okay, it is equal to 5,95,000 something. So it is too much. 595. Okay, 595, 554.96, 96 joule per kg. Okay, if the question has asked it in kilojoules, so you should have you should have divided it by thousand, right? So we have got our heat added, which is equal to 595, 554.96 joule per kg. Okay, so this much heat was added to make the flow choked, was M1 is choked, M2, right? So we got the story. Now the last question for it, let's see. Okay, okay, okay. So the last question. See, what will be the pressure ratio of exit by inlet? So it's easy. We have the direct formula. P2 by P1 is equal to 1 plus gamma M1 square upon 1 plus gamma M2 square. Okay, so you should check what is asked. P2 by P1 is asked, and this formula is for P2 by P1. If P1 by P2 was asked, so you should have used this formula and just made it inverse, or you can directly use the inverse formula as well. So P2 by P1 will come as 1 plus 1.4 into M1, which is 3 square upon 1 plus 1.4 into 1 plus square. Okay, so it will be 1 plus 1.4 into 3 square divided by 1 plus 1.4, right? And that's it. So 5.67 is the answer. So P2 by P1 is equal to 5.67, and that is all. So we have completed all the questions now for this PDF. Yep. So like using whatever we have discussed here, like whatever I have told you how to approach the question, you can think of that thing as well. Okay. Like first I was thinking some different approach for this question, but then I got reminded of this T2 by T1 formula, and like when you'll be practicing, when you'll be revising, so these formulas will be very much handy to you, like very much like remembered by you, and you can use them based on the problems you are seeing. So yeah, uh, if I'll be having different questions, After it, I'll be making some more videos over them. Okay, so that's it.